Hello everyone, nice to talk to you again. So this class we're going to continue our topic on the fundamentals of environmental engineering and sciences. But before we start the new contents, I think it's necessary that we go through some of the important concepts that we have learned about during the first quarter of our class. And also I would like to go through the exam problems with you again, okay? So here I'm just going through some the problems that some of you have questions about, and I just want to highlight the logic behind these problems. For example, the first problem that I saw is that quite many of you have troubles in understanding this problem. It's asking which of the following has the highest density. So I'm not asking you to check the periodic table or check the material properties from a textbook. And also, since we don't have the textbook during the exam, it's quite difficult to find out which one is it. But basically, I want you to look at the properties of each item here. So I provided the materials, for example, the iron, platinum, or diamond. I saw quite many of you chose a diamond here. But if you further look at the problem, there's a weird thing in here, right? There's a proton. So basically, if we consider the density of a material, so the material is composed of atoms, right? And in an atom, most of the volume is actually occupied the electrons, while you have a nucleus in the middle that's containing the protons and neutrons, and this thing, the neutron, contributes almost all of the mass, right? So if we consider the density of any material, actually the nucleus will have the highest density, or the protons or neutrons will have the highest density. So it turns out that actually the density of a proton is around 10 to the 18th kilograms per meter cube. All right, which is much higher than the other materials. It turns out that actually the Earth's total mass is around 10 to the 24th kilogram, which means that if we can get 10 to the 6th meter cube of this material, or of this proton, it's actually the same as the mass of the Earth. But how large is 10 to the 6th of meters cube? It is almost the volume of our building, right? The Butler Carlton Hall. You can think of that as 100 multiplied 100 multiplied 100 meters, right, on each side. So it's not a large volume. I would say it's a very small volume, and actually contributes, or it is equivalent to the entire mass of the Earth. So now you can see that actually the proton will definitely have the highest density, right? And then the second problem is about the calculating the normality of a material. So maybe I wasn't very clear on the class. So basically the molarity, let's start from the molarity. So molarity is the quantity of certain species that's dissolved in the water, and it's showing with a unit of mole per liter, right? For example, if we have 0.1 m or molarity of the sodium carbonate, it simply means that the concentration, or the molar concentration of the sodium carbonate, is 0.1 mole per liter. Okay, so this is what it means. But in terms of the normality, it's actually defined as the number of equivalents per liter. So how do we understand this equivalent here? So more specifically, let's say we're talking about the sulfuric acid. Okay, so for sulfuric acid, it is actually providing, for each mole of the sulfuric acid, it's providing 2 mole of the protons. And the protons are understood as the equivalents of the sulfuric acid. So specifically, or a more general definition of the normality is calculated by this special Z number multiplied by molarity. Okay. For example, if we're talking about this 0.1 m of the sodium carbonate, then the normality of this sodium carbonate is going to be Z multiplied by this 0.1 here. Then how do we calculate this Z here? So furthermore, for the acid or base reaction, for example, the sodium carbonate can react with the proton ions, right? So the Z here is the number of protons it can uptake or release. So for each mole of the sodium, for the sodium carbonate, it's going to react with 2 moles of the proton ions, right? It simply means that Z should be equal to 2, okay? If Z is equal to 2, then the normality of the sodium carbonate is going to be 0.1 multiplied by 2, and it's going to use the unit of N here. So that's why for this problem, we're going to choose B here. This is talking about the acid-base reaction. So there can also be oxidation-reduction reactions. And for oxidation-reduction reaction, the Z is the ability to uptake or release electrons. So under that situation, for example, if we're talking about iron reacting with oxygen, so that's going to be, okay, it's going to be 2/3 O2 reacting to form, let's say here, reacting to form iron oxide, okay? For each mole of the iron, it's going to require 3 electrons, or it's going to contribute 3 electrons, right? So under this situation, for the iron, the Z is equal to 3, okay? So this is how we calculate the normality from these problems, all right? And then further is the calculation of the equivalent weight, okay? So for the equivalent weight, it's calculated by the molecular weight divided by Z. So if we know the Z value from here, then we can calculate what is the equivalent weight for any compounds, right? For the calcium carbonate, it has a molecular weight of 100 grams per mole, okay? So for each mole of the calcium carbonate, it's going to react with 2 moles of the proton ions, right? And because of that, the Z is equal to 2, and the equivalent weight is equal to 50 grams per equivalent, okay? So also notice that the unit for this equivalent weight is going to be like this. And similarly, if we are talking about the sodium carbonate, we know that sodium has a molecular weight of 23, right? 23 multiplied by 2 plus 12 plus 16 multiplied by 3, that's going to be 106, okay? So the equivalent weight of the sodium carbonate is going to be 106 divided by 2, which is 53 grams per equivalent. Right? So this is how we can calculate the equivalent weight. And so if we go to the part 2 of the exam, I think many of you can understand or can calculate that problem on the reactors and also the hydraulic conductivity. So here I'm just trying to go through the alkalinity part here. I have to stress that the alkalinity is an important part throughout the course of this subject, throughout our course, okay? So I really want you to understand how we can calculate alkalinity here, okay? So the alkalinity basically represents the acid neutralizing capability, okay? So because of that, we have to consider all of the species that are able to neutralize acids or neutralize or react with the protons. So if the water contains carbonate species, then the alkalinity is calculated by the concentration of the bicarbonate plus 2 multiplied by the concentration of, or the molarity of the carbonate ion, plus the concentration of the OH ion minus the concentration of the proton ion, okay? And this will give us the unit in the equivalent per liter. And normally we will convert this alkalinity to the mass, or basically show that as calcium carbonate. So we have to further multiply by the equivalent weight of the calcium carbonate to get the alkalinity shown as calcium carbonate. So because of that, the first step we calculate this problem is first to calculate what are the molarities of the bicarbonate, carbonate ions, and OH ions. So what we will do is we'll use 2 divided by the molecular weight of sodium hydroxide, okay? So that's going to be 23 plus 16 plus 1, all right? That's actually 2 over 40, okay? So this is gram per mole, which we can represent as m, okay? And then for the sodium bicarbonate, that's 1 gram, and then we'll divide by 23 plus 1 plus 60, okay? That is 84 m, okay? And then we also have the sodium carbonate, which is 1 over 23 multiplied by 2 plus 60. We already calculated that. That is 106. Okay, so after we get these molarities, we need to plug those in to basically calculate the alkalinity that's shown as equivalent per liter. Okay, so we can add these on, add all of these up, right? We have 2 over 40 plus 2 multiplied by the molarity of the carbonate ion, which is 1 over 106, plus what? Plus the OH ions. Okay, that's 2 over 40. So the first one for the bicarbonate, it is actually not 2 over 40. It should be 1 over 84. Okay, and you may ask why we ignore the hydrogen ion. It is because the solution is mainly composed of the hydroxide here. So because the pH of the pH for these base solutions is going to contain very few hydrogen ions or proton ions, so we can directly ignore that part of the information. So by calculating that, we can find out that it is actually what? It is actually 0.081 equivalent per liter. Okay? And then we can further calculate. We can further calculate what is the alkalinity here. Okay? So we can further multiply this value by the equivalent weight of the calcium carbonate, which is 50 grams per equivalent. Okay? So we can find out that this is actually around 4 grams per liter as calcium carbonate, or 4.04. Okay, so the question asks us what is the alkalinity shown as a milligram per liter. So further we can multiply this value by 1000 to show that as milligram. That is 40 milligram per liter as calcium carbonate. So this is how we can calculate the alkalinity based on the concentration of all of these solutions, right? And basically, if you follow this step, you can calculate them one by one to find out what is the alkalinity. And actually, an interesting problem that we had at the as the final question is actually wants us to calculate what is the concentration of the aluminum in a solution. Okay, so this is involved with the or this is related with the solubility product of a sediment or of a compound. Okay, so again, if we go back to the solubility equilibrium, then we can find out that what actually happens is, let's say if A is in sediment, it's going to dissociate into B plus C. Okay, so the solubility product Ksp is actually equal to, let's say, AB multiplied by Cc. Then it's going to be equal to the concentration of B ion to the power of B multiplied by concentration of C ion to the power of C. So for this specific reaction here, the solubility product should be equal to the concentration of the aluminum ion multiplied by the concentration of the OH ion to the power of 3, right? And furthermore, we learn from the textbook that the Ksp, or the pKs, is calculated by log 10 of the Ksp. So or minus log 10 of the Ksp. So what that means is that the Ksp is going to be 10 to the minus 23.9. Okay, and further we need to find out what is the, so since the problem wants us to solve for the concentration of the aluminum ion, right? This is what we're trying to get. So we need to find out what is the OH concentration. And the problem states that the pH of the water is gradually controlled to be 5. Okay, if we know the pH gives us the concentration of the hydrogen or the proton ions, right? And then based on that, we can calculate what is the concentration of the OH ions. So basically, if we know the pH is 5, it simply means that the pOH is equal to 9, right? And then if we have that, then the OH ion concentration is going to be the 10 to the negative 9 m. Okay? So because of this information, we have the aluminum ion concentration multiplied by 10 to the minus 27, right? That's to the power of 9, right? And further to the power of 3. So that's going to be minus 27 equal to 10 to the minus 32.9. Okay? Further, it will give us the aluminum ion concentration is equal to 10 to the minus 5.9. All right? And furthermore, based on the concentration of this aluminum ion, which is shown as molarity, we can further calculate what is the concentration of the aluminum shown as milligram per liter. So it turns out to be, I think it's 0.038 milligram per liter. Okay. So there's one interesting feature we find actually. Let's say if the solution is controlled to a pH of 7 here, which is the pH of normal water. So you can actually find out what is the concentration of the aluminum ion, right? So instead of using 9 here, negative 9 here, we're going to plug in negative 7, which is going to give us a new value of 10 to the negative 21, right? And then you can find out that aluminum ion concentration is going to be 10 to the minus 11.9, which is extremely low. So this means that the aluminum ion can actually only exist in a low pH solution instead of neutral or high pH solution. So if it's under neutral or high pH, these aluminum ion will just combine with the hydroxide ions and form these sediments. And actually, we're using this information to clear the water, or to to use aluminum as a ingredient to control the water quality. Okay, so we're going to learn about that in this class. So before we introduce the new contents, and actually this is all about the exams that we had. I think many of you already grasped the contents, but maybe you're searching for other, you're quite puzzled or confused by a lot of irrelated information. For example, here, the problem is also giving you the concentration of the aluminum ion initially, but it doesn't really play a role in the problem. So similar, same for the other questions here. I think many of you are grasping the idea here, but it's just maybe you're bothered by other contents. So I'm pretty sure that if you can go through the homework problems and understand the logic behind the problems, you should be able to do fine in the future exams. Okay, so now let's go back to the contents of this class. Last class, we introduced a new concept, that is the dissolved oxygen, or DO Sag curve, right? The reason why we call it as a Sag curve is because the dissolved oxygen concentration after mixed with the wastewater, the concentration is going to decrease and then go back, right? And we showed that the final DO concentration is going to almost get close to the saturation dissolved oxygen concentration, or the DOS. Okay, so we showed that the reason why we are seeing this Sag curve is because of two processes. One of them is a deoxygenation, which is because the oxidation of these organic species by the microorganisms. And there is also a process that's actively pumping oxygen into the water, which is called as the reaeration process, right? The oxygen is being added into the water body all the time. And then basically we can construct a differential equation and try to solve for the DO concentrations as a function of time. So to calculate the DO, first we need to find out what is the dA and LA, which is basically the oxygen deficit and also the remaining BOD at the initial time, right? Because we know that the differential equation is actually calculated by dd dt is going to be equal to, let's say, minus KRD and then KDL, right? We need to know what is the initial condition for the L, which is the remaining organic compound concentrations there, right? We can calculate these terms by using the mass balance, okay? And then we should plug in all of those contents into, or all of those information into this single equation here. Okay, you don't have to memorize this, but you should be able to use this and then calculate the correct answer from the homework problems. Okay, so we need to use the reaction rate constant of the deoxygenation, rate constant of the reaeration, right? And then we need to plug in the concentrations of these organics or at the initial condition. And then if we want to calculate the oxygen deficit at any time, we can just plug in the time information. But more commonly, we're going to evaluate the oxygen deficit at certain distance from the mixing point. And therefore, we have to convert this distance into time by using distance divided by the velocity of this mixture or the river water, and then to calculate what should we plug in as this parameter in the equation. Okay, so this is the contents of the last class. So last class we also left something at the end, which is the groundwater quality. So basically introduce the ocean water quality, lake water quality, estuary water quality, right? So the final one is the groundwater quality. So the groundwater quality is affected by quite many sources. For example, the septic systems or leaking of the ground, underground storage tanks, right? Spills, accidents, leaking, landfill. So landfill can really pollute the groundwater quality by just, if you're having rain or precipitation, these water are going to can get leaked into the groundwater and affect the water quality there. And for example, also the leaking or retention ponds or leaking retention ponds or the lagoons. Okay, so for the groundwater quality, a quite important concept is to understand how fast some contaminant can flow within the groundwater. Okay, so we need to understand what is the transport of the contaminants. So there can be water-soluble chemicals which can easily move with the groundwater. For example, if there are ethanols or methanols, they're very miscible with the water, so they can almost travel at the same speed as the groundwater. There can also be some non-aqueous phase liquids, so they can be gas or PCB, which can travel at a different rate here. So basically, for most of the contaminants, they will move at the same rate or a little bit slower than water, which is because of the absorption by a lot of the rocks or sands there. Therefore, people defined a parameter called the retardation coefficient. Okay, so just by this name, you can see that basically the retardation coefficient describes how slow the contaminant will flow in the water. Okay, for example, we have a block of sands here, and water can go through, and there can be other species, for example, some organics, which are contaminants. They can also flow with the water, but because of the sand here, they're going to get absorbed. And then, because of that, the organics are going to are not able to flow as fast as the water there. And we call this process as a retardation, right? The retardation coefficient is calculated by the velocity of the water divided by the velocity of the contaminant. For example, if the water can flow at a speed of 10 meter per second. And then the contaminant can flow at a speed of 1 meter per second because of the absorption. Then the retardation coefficient is 10. So basically, the higher the retardation coefficient, the slower the water can flow within the underground water. Okay? So let's go through an example here. For example, if we have, if we're talking about two different houses, okay? And let's say we're neighbors, and I am living in the house A, you guys are living in the house B, okay? So I'm doing something bad to the groundwater, dumping some trash into the ground somehow, because groundwater is also way below the surface, right? So I'm introducing some contaminants here, okay? And the contaminants are able to flow with the water, and we want to estimate how long does it take for the contaminant to travel from point A to point B. So this is the scenario where we have to consider about the retardation coefficient. Let's say our two houses is separated by 60 meters, okay? And then the linear velocity of the water is 4.7 multiplied by 10 to the minus 6 meters. And the retardation coefficient of this contaminant is 2.4. So because of that, we can calculate the retardation coefficient of, or the velocity of this contaminant, which is 4.7 multiplied by 10 to the minus 6 divided by this retardation coefficient, right? Because the higher the retardation, the slower the slower the contaminant can flow, right? Meter per second. And then we can directly, if we want to determine the time that's required to reach the second house, right? We can just divide the distance by the contaminant velocity, which is 60 divided by 4.7 multiplied by 10 to the minus 6 divided by 2.4, right? And this turns out to be 354 days. So you can see that 60 meters is not a very long distance, right? And it takes almost a year for the contaminant to reach to another location here. So you can see that really the traveling of these contaminants in the underground water is relatively slow. Okay, so that's all about the water quality, which is the chapter 9 of our textbook. Okay, so this class we're going to go to a new chapter, which is the chapter 10, and about the water treatment. Okay, so as I've introduced in the first class, when we talk about the water treatment, we represent the drinking water treatment. Okay. So for the wastewater treatment, we call that as water treatment specifically. When we talk about the water treatment, it specifically means for drinking water treatment. Okay, so here we can do a brief overview of the water treatment. So if we talk about the water sources, there can be many sources, right? So for Rolla, most of us are using the deep wells. Okay, it's from the it's actually the groundwater. So for the groundwater, it's actually relatively clean, but the major thing that's making our lives harder is because of the hardness. We call that hardness. It's basically the concentration of these ions here. For example, calcium and magnesium. So whenever we say that some water is hard, we have a standard, right? So if the water is hard, you're able to saw those white residues whenever you are trying to boil some water, or you can see that or find them from your sink. Okay, so the more severe that is, the more hard the water is. Okay, so more specifically, the hardness is actually related to the concentration, or can be calculated by the concentration of these ions here. But if we're talking about the sources of water from the shallow wells, or rivers, lakes, or reservoirs, then the water quality is not as good as the groundwater, actually. And because if it's more accessible to the surface, then some bugs or bacteria, virus can also get deposited in there. And also, if it's also easier for some chemicals to flow into the water and then cause some trouble there. Okay, so for the surface water or for these rivers or lakes, it typically will need more treatment. Okay, and whenever we talk about the drinking water quality, there are several standards to describe the water quality, right? So when we talk about, when we say that the water quality is bad, it's either based on the appearance, right? And by saying appearance, we mean the color, the odor, the turbidity, and the solid, okay? or any, if there are any solids. So if anyone hand you a cup of water that looks like milk, you won't drink that, right? Because the color doesn't look right. If you smell it, it smells really bad, you won't drink it either. And it's also very turbid. You don't know what those white things are, right? Those turbidity, it might be chalk, right? And if you can directly see some sediments in the water, we're also quite concerned about the water quality there. So apart from the appearance, people also want to know whether there are pathogens, for example, bacteria, protozoa, viruses, or so on and so forth. And actually, the pathogens is a very important item that has been puzzling the modern population a lot, right? So in the first class, we talked about that there are two scientists in the Great Britain who discovered that the water quality is bad because of the bacteria inside, because of the E. coli there. So that promoted the disinfection of the water, which can kill these pathogens. And there can be some organic pollutants, for example, pesticides. Those things can kill bugs, and they can also kill people. There can be inorganic pollutants, for example, heavy metals. And there can be disinfectants or disinfection byproducts or radionuclides, right? Radioactive materials in the water. Therefore, we have to treat the water quality so that they can be as good as the drinking water quality. So they can be drinkable or potable, okay? And also the EPA promulgated some standards describing the water quality. All right, so we have the standard called the maximum contaminant level, which is MCL, and that's enforceable for the managing the water quality. And these are for the regulated substances. And there's also a parameter called the maximum contaminant level goal. Okay, so that is the target that we're trying to reach. And after about the introduction for the water quality concerns or water quality standards, we need to talk about how we treat the water quality. Okay, so there can be, for example, if we're talking about the pathogens, we have to do disinfection to kill all of these pathogens. If there are debris or sedimentations, we need to use some screening to first clean these particles or clean these solids before we drink it. If there are heavy particles, we can just let them settle down or sit still, right? To let these certain particles to settle, and then we can get rid of them. So when we talk about the disinfection, here I'm actually listing a chart that's describing how the disinfection or how the chlorination actually affects the human health. You can see that at the end of 1900, actually, as close, maybe it's 1908, people started to use the chlorination to purify or to disinfect the water. And as soon as people did that, the typhoid fever, or the number of the death rate for the typhoid fever decreased exponentially. Okay, so you can clearly see that disinfection of these microorganisms really help people promote their lifespan or promote how people live in the modern time. Okay. So here we talked about the microorganisms. We're going to use disinfection, debris, we'll use screening, heavy particles, we can use settling. So there can also be some colloids or suspended solids. For example, the milk, right? Milk looks like jelly, right? And although we know that it's mostly composed of water, but because of these organics, which are suspended in the water, it's giving it the milk the white color. So they are suspended solids, and we can try to use some methods um, to remove or to let these components to settle down. Okay, so we call this process as the coagulation, flocculation, and clarification. So coagulation means to let these suspended species to collide with each other, right, and then form these larger particles, and then they can further settle down and at a certain rate. And furthermore, we can filter out by clarification. And in terms of the smaller particles, we can use the sand filtration to remove these particles. And specifically for the groundwater, where we are having a lot of issue with the hardness, for example, the metal ions are too high, we can use the softening, which basically means that we're adding carbonate into the water to remove these ions. Okay, and there can also be some dissolved organic pollutants, for example, odors. We can use activity carbon to absorb these species, or we can use air stripping to remove these um, organic pollutants from the water. Okay, so here I'm showing a schematic diagram of a modern time water treatment plant. So the fonts here are a little bit small, but I can zoom in to let you see more clearly. So basically the process starts from the left-hand side, left top corner, okay? So this water treatment plant is using the surface water directly coming from the lake, right? So we're going to use a intake pipe, right? So it's going to go through some preliminary treatment. For example, the protective bar screen will remove the debris from the water, right? If there are some larger solids, also you don't want fish to get into the pipes here. And then we also have the traveling water screen, which is going to have a smaller mesh size to remove a little bit smaller particles. And then after we'll inject them into this low lift pump well. Okay, so it's a larger reservoir, and then by meaning low lift pump means that the pump will require less of the power to transfer these liquids or these water into the pipeline. Okay, we can process a large amount of water, and it doesn't need a lot of power. And then after the water injected into the pipeline, first we'll go through the pre-chlorination to remove some of the, or most of, a fraction of these microorganisms, so that they can get into the solid state, get into the solids, and then further we can remove that from with these following processes. We'll inject the chemical coagulants. So later on we'll introduce that these coagulants, we're basically using the aluminum ion to remove these coagulants. The reason why we use that, we can further introduce later. And we call this process as coagulation, right? We can remove these suspended colloids from the water. And then the flocculation simply means that we'll further let these particles to settle down, and then to basically form larger particles, so that it's easier to get rid of. And further, we'll introduce them into this sedimentation basin, where the larger particles will have enough time to settle down to the base. And then after that, when we get further cleaner water, we'll introduce them into the sand filtration, or the sand filter, to remove the smaller particles and also the particles generated from the flocculation process. And after they're filtered, we introduce them into the post-chlorination to completely remove these pathogens, bacteria or virus. And we also have the fluoridation. So the fluoridation simply is trying to add fluoride into the water to protect the teeth of the people, especially the younger children, right? To help them protect their teeth. And then after the fluoridation, we basically finished all of the water treatment process. And then what we do is that we can store these treated water, for example, to use this high lift pump. Okay, so remember initially we had this low lift pump, which consumes less power. The reason why we use high lift pump The reason why we use high lift pump is to want to lift it up to a higher elevation, right? To store all of these water, and we can also store them in the ground level reservoir, right? And then finally we introduce the water into the distributed system, and then they can be introduced into all of the households. We can enjoy these drinking water. So I also have a short video which can give you another brief overview of the water treatment plant. So I have to mention that 2 weeks later, we're going to visit the water treatment plant in Fort Leonard Wood, and that's going to be a tour lab. Okay, so we're not going to do the lab in the classroom, and we're going to look at these process in more details. Okay, so here this video is about the tour to a water treatment plant, but it's going to be a little bit different compared to the water treatment plant we're going to see, and there might be some differences from this schematic diagrams too, but the major components are the same. Okay.
Welcome to our tour of Winnipeg's drinking water supply and treatment system. We use leading-edge technology to treat the water as it passes through many stages, including coagulation, flocculation, dissolved air flotation, filtration, and 3 types of disinfection. Our system protects public health by virtually eliminating the risk of waterborne disease and reducing the level of harmful disinfection byproducts. It also improves the taste, odor, and appearance of our tap water. Shoal Lake has been our source of water since 1919. It's located 136 kilometers from Winnipeg at the Manitoba-Ontario border and is approximately 92 meters higher than Winnipeg. Water flows downhill from Shoal Lake through an aqueduct into 4 large reservoirs next to the treatment plant. The aqueduct is a large concrete pipe that carries up to 386 million liters of water per day to the reservoirs. The reservoirs hold up to 8.8 billion liters of water, which on average is enough to supply Winnipeg for about 30 days. Water flows from the reservoirs through 2 large pipes into powerful pumps that move the water into the plant for treatment. This $300 million state-of-the-art facility features a highly automated system that monitors and controls a wide variety of instruments, mechanical equipment, and electrical equipment, including 40 processors, 140 pumps, 2,300 valves, and 1,400 instruments. It can treat up to 400 million liters of water per day. In this first step, we add sulfuric acid and ferric chloride as the water flows into the plant. Sulfuric acid lowers the pH of the water and makes this stage of treatment more efficient. Ferric chloride, a coagulant, causes the naturally occurring particles of organic material in the water to attract each other. The water enters flocculation basins, where large mixers slowly stir the water, causing the particles to collide and stick together, creating large clumps. Now that large clumps have been formed in the water, the next step is to remove them. We do this in dissolved air flotation tanks. We inject a stream of water, supersaturated with air, into the flocculated water which is flowing into the bottom of the tanks. Tiny air bubbles are released into the water and carry the clumps to the top of the tanks. Skimmers remove the floating clumps from the surface of the water. The clumps are pumped to an area for further processing. The treated water is collected from the bottom of the tanks. The water flows from the dissolved air flotation tanks to chambers where ozone is added. This step, called ozonation, does 3 things. It provides the first level of disinfection by destroying most of the harmful bacteria. It improves the filter performance in the next treatment stage, and it improves the taste and odor of the water. We make ozone by applying electricity to liquid oxygen. At the end of the ozone chambers, we add sodium bisulfite to the ozonated water to remove any leftover ozone. The water now flows into filter tanks containing biologically activated carbon. The filters remove any remaining small particles in the water, including parasites. Good bacteria growing on the filters remove some of the remaining dissolved organic material. This reduces the level of disinfection byproducts in the water. We clean the filters regularly by pumping air and water backwards through them. The backwashed water is pumped to an area for additional processing. The filtered water flows into the chlorine contact chamber for a second round of disinfection. We add chlorine to kill viruses and bacteria such as E. coli that might be in the water. Chlorine is the most widely used drinking water disinfectant in North America and has been used for more than 100 years. We then add sodium hydroxide to bring back the pH of the water close to the original level. The water flows from the chlorine contact chamber into an underground reservoir called the clear well. We disinfect the water once again using ultraviolet or UV light. We pump the water through 6 stainless steel chambers, each containing 9 ultraviolet lamps. The lamps are similar to fluorescent bulbs. With only seconds of exposure, the UV light rays penetrate any remaining parasites, such as Cryptosporidium or Giardia. The UV light renders these parasites harmless. After UV disinfection, the water flows into 2 large pipes where we add fluoride to help prevent tooth decay. We also add orthophosphate to form a protective coating inside water pipes. This coating helps reduce corrosion that may add lead to tap water. The 2 large pipes carry the treated water to our 3 reservoirs and pumping stations in the city. We add chlorine again as the water is pumped into the distribution system to ensure that the water remains disinfected until it reaches your tap. The final stage of treatment is to deal with the materials removed from the water by the treatment processes. The backwash water from the filters is allowed to stand until the solid materials settle. We then send the clean water back to the beginning of the treatment process. We pump the settled out material from the filters and the clumps of particles from the dissolved air flotation process to outdoor settling ponds next to the treatment plant. The pond contents go through natural freeze-thaw cycles, which separate the liquid and solids. We pump the liquid into Winnipeg's sewer system for wastewater treatment and take the solids to the landfill for disposal. We test our water each step of the way, from Shoal Lake to your tap. Our testing program includes over 150 different tests at more than 130 different locations throughout the year. Because water quality is so important, we do more testing than the provincial government requires. Our certified professional team is dedicated to ensuring that our community enjoys safe, high-quality drinking water that meets provincial regulatory requirements and falls well within Health Canada guidelines. We hope that you've enjoyed this tour of our drinking water supply and treatment system.
Okay, as you can see, the detailed structure of the drinking water system is quite different from what we have learned from the sketch, and also it's going to be quite different from the water treatment plant that we're going to see. But actually, they're going through similar steps. So first, they have to go through the coagulation, right? They have to go through first some pre-treatment, for example, to add some chlorination or add ozone to the water to remove some or to achieve the disinfection purpose. And then they will go through the coagulation or flocculation process. And then either we can use sand filtration or use filter to remove these smaller particles, right? So mainly the major steps are still quite similar. All right, so we can go through some important steps or these critical steps during the drinking water treatment process. So the first important step that we have to know is about the coagulation and flocculation. Okay, so what this does is to remove the colloids in the water, which is basically the components we're talking about. The milk is going to be the components suspending in the milk, right? So what this does is going to remove the turbidity, color, and bacteria. So the reason why these colloids are suspending in the water is because because it's very small, okay? So normally they're negatively charged. The reason why they're negatively charged is mainly because of their compositions there. And since they're likely charged, they're going to repel each other, right? So they're not going to be able to collide into larger particles and further settle down. And at the same time, the Brownian motion of these very small particles keep pushing them moving around, so then there's no way that they can really collide to each other and then settle down. So the method that we use to remove these to remove these components is to introduce the coagulants into the water. Okay, so what this coagulant does is actually remove these or neutralize these surface charge. So since these colloids carry negative charges, we can introduce some species that carry positive charges. And the components we're talking about are mostly the ions that's carrying more charges or in a higher valence state, right? It can be either aluminum ion or ferric ion, okay? So after these ions basically interact with the colloids in the water, they can get in contact and then they can start to neutralize the charge. And then there is no barrier among different colloids, and they can stick together and form larger settlable particles, right? But the thing is that if we add too much coagulant, it's going to make the particles all carry positive charges, right? So that's going to reverse the charge, and then it's called restabilization. Simply means that these colloids are going to get resuspended in the water. So we want to put the right amount of the ions into water, or right amount of these coagulants into the water to remove these colloids. So here is what I'm trying to talk about. So basically, these particles or these colloids in the water, they're going to carry a net negative charge, okay? And because of this negative charge, surrounding the particle is going to be a layer of ions that's carrying positive charge, right? Because if in the water there are many types of negative ions, and these ions, positive charged ions, are able to attach them to the surface of these negatively charged particles. So that's going to form a stable layer of the ions. And further outside this positive layer of the ions, there's going to be another layer of ions that are carrying a net negative charge because of their attraction. So this is the reason why that the particles in the water, they're really protected by multiple layers of the ions. It's very uneasy, or it's very difficult for other ions to touch, or it's very difficult for other colloids in the water to touch these particles and form larger settlable particles. So the method we use is, as I have introduced, we can introduce these aluminum ions or ferric ions, right, to let them interact with these colloids to form these larger particles. Okay, so here is more introduction on the coagulant. Okay, so the coagulant can either be aluminum or iron salts. So for the aluminum, we can use the aluminum sulfate. We also call them as alum. Okay, so the main composition is basically the aluminum sulfate. Sometimes they can get attached with the water too. And once these aluminum are introduced into the water, because of the pH of the water, okay, so this goes back to the problem that we talked about in the beginning. So these aluminum can react with water to form this aluminum hydroxide. Okay, at the same time, it's going to release these proton. Okay, and because of these aluminum hydroxide are sediments, and they're carrying more positive charges, they can interact with these colloids in the water and form these coagulants and further settle down in the water. And therefore, for using these aluminum ions, the best pH range is actually on the acidic side. You can see the neutral pH is around 7. So the best pH range is on the acidic side. Okay? And if we can further increase the pH, that will help us create higher or larger flux, simply because we're going to form more of these aluminum hydroxide, and they can further interact with these colloids in the water. And for these iron salts, we can use the ferric sulfate or ferric chloride. And similarly, these salt ion or iron salts or the ferric ions are going to react with the water and form this ferric hydroxide. And further, this ferric hydroxide can interact with the colloids and basically form larger particles or settlable particles. And you can see that the advantage for using these ferric sulfate or ferric chloride is that we can operate the system in a wider pH range. And apart from introducing these coagulants, we can also add some other steps to further promote this coagulation process. We can add activated silica, right, or add clay or a return sludge and polymers. So basically, the reason why we add these is to make the water more turbid, or to make it more colloidal, so that once we form these smaller particles, it's easier for them to further interact with small particles. We're going to form larger flux or larger particles, and it's easier for them to settle down. And we can also adjust the alkalinity, so basically to push it to a more basic side, right, to promote this reaction, to form more of these hydroxide, and then they can interact with the colloids in the water to form the solid particles. So we can introduce the lime, right? The lime are basically calcium hydroxide, right, or the calcium oxide, to enhance the pH, and then let the coagulation to happen more quickly. Okay. So apart from the coagulation or introducing the coagulants, one thing we have to make sure is that these coagulants rapidly mix with the water we're trying to process, right? So the rapid mix, what the rapid mix does is it can quickly disperse the chemical to particle surface, and then to change the surface or to realize the surface neutralization. So the degree of the mixing is actually measured by the velocity gradient. For example, if we're using these propellers in the water, then the velocity at the center is going to be the lowest, while the velocity at the outside or the tangential location is going to be the highest, right? And here the velocity is 0, and then we can calculate what is the velocity gradient. That is just by using this velocity divided by the distance here. Okay, so the degree of mixing is parameterized by this velocity gradient. And here it introduces different types of mixers. You can have these turbine chamber or propeller chamber. So these are mainly the detailed design for these mixers. You can have double compartment, so parallel to each other, or it's either up and down, right? You can use two bed pedals or inline blender. So these are the detailed designs for these rapid mixers. Okay, so that's all for the contents of this class. So let's finally do a quick review of the contents. So basically, we want to know what are the major water quality concerns, what is the conventional drinking water treatment process, what are the colloidal materials that are not settled in the water, right? Why coagulants can get destabilized, or they can destabilize the colloid materials, right? And what chemicals are used as the coagulants? This is quite important. We can use aluminum ion or ferric ion to realize the coagulation. What are the coagulant aids, and why do we need the rapid mixing? And what is parameter for quantifying the mixing intensity? Okay, so that's all for the contents of this class. Feel free to let me know if you have any questions. Thank you.